I'd like to describe to you the high energy density physics research at Sandia National Labs. And I guess you're advancing the slides? Or, oh, like that, okay. So I wanted to give you a little summary overview picture of the labs, Sandia National Labs. And I'll point out it is Sandia National Laboratories, and it's a government-owned, contract-operated, commonly called a GOCO facility operated by Lockheed Martin. For years, we were part of AT&T Bell Labs. I think Lockheed Martin took us over in 1992 or 3, something like that. And Sandia currently has about 9,000 career employees. There's contractors on top of this, and I forget exactly how many of those there are. But in terms of career employees, is 9,000, and we have an operating budget of approximately $2.5 billion. And the major locations include Albuquerque, New Mexico. There's roughly 8,000 people there, and close to 925 employees at Livermore, California, which is right adjacent to Lawrence Livermore. It's across the street to the south. And Sandia's precursor was Los Alamos National Labs Z division. You're going to hear me talk a lot about Z, but this Z division's not. But we were created in 1945 as part of the Manhattan Project. But Sandia separated from Los Alamos in 1949, and AT&T took over its initial operation at the request of President Truman. So we were sort of born out of the Manhattan Project, but we became our own lab in 1949. Sandia broadly contributes to the national HEDP and ICF programs in a number of important areas. And Sandia leads the national effort in pulse power, high energy density physics, and ICF research. Sandia operates the Z and Z Beamlet laser facilities. This was the prototype actually for the NEF. This is one set of beams from the NEF. It was moved from Livermore to Sandia, and we've been using it as a backlighter, and now we're developing a petawatt capability on that laser. So it's one of the largest lasers in the world in its own right. And since 1995, the Sandia programs participated and contributed to the NIF diagnostic effort. And Sandia is now still engaged in the NIC efforts through in the areas of laser physics and shock timing. So we are truly national contributors across the ICF, and Sandia programs now actively developing a fundamental user program on Z and Z Beamlet. And the Sandia HEP and ICF employs approximately 155 technologists and technical staff, plus another 80 contractors. So that was sort of an overview. And if you came by our laboratory poster session there, I mean, we talked a little bit more about the broad Sandia. So now I'm drilling in. Sandia is a very comprehensive national lab, so you have to understand this talk is going to drill into the HEDP parts of it. So let me move on. So the regime of high energy density physics or of high energy density are typically associated with energy densities of 10 to the 5th joules per cubic centimeter and 1 megabar of pressure. And this is one of these classical plots showing temperature and number density, showing how a lot of things fit. You know, the typical ICF hohlraum physics such that you're doing on NIF, we're doing on NIF, is the 10 to the 8th temperatures. You know, and by the way, the densities here are in meters cubed because I think a magnetic fusion person made this poster, but so bear with that. But and if you look to see the regimes that we're working with at Sandia, we do isotropic compression experiments, and these are and flyer plates, and this is related to dynamic materials work, which Richard here is a part of. You just finished a run, last week, right? Wednesday, yeah. So yeah, and so the other region that we're dealing with is Z pinches, which are typically put you up in this part of the plot. And I'll just say this, and I'll talk a little bit more. Z-pinches are a classic plasma physics system. Z-pinches was the first magnetic fusion program, and it just for fun, it's interesting. It was the first Z-pinches in the U.S. were at Los Alamos, and it was called Project Sherwood, and it happened in the early 50s, and it was a classified project. And the reason was it was proliferation. It was a cheap source of 14 MeV neutrons, if it had worked. So they classified it on that basis. And you might wonder where the word Sherwood came from. Well, James Tuck, he's not exactly Friar Tuck, but he was the head of the group at the time. And so there's the history, the Project Sherwood and the James Tuck. It's sort of an interesting. So we're, in some sense, with modern pulse power technology, we're revisiting all of this physics once again. And so it's sort of an interesting thing. So several recent studies have highlighted high energy density science. Some of these are not so recent now, but Ron Davison put this thing. I'm just putting this out here. These books are available. Maybe a lot of you have already read those, but and there's probably some that are even newer than this view graph. So Z has a unique role as one of the 3 major US facilities for high energy density physics experiments. And of course, these facilities are NIF and the Z facility and the Omega and Omega EP facilities at University of Rochester. And there's scale here. This bar is about 120 meters, and the diameter of the Z machine is about 33 meters. So it gives you a scale of the size of these facilities. And so the interesting thing is, after 40 years of research, the components of simulators or simulation codes, drivers, and diagnostics and targets are in place to test ignition concepts. And Kim talked a little bit about what was going on NIF and that front. And so it's an exciting time. So Z is the world's largest pulse power facility. You've seen the lightning bolts here probably often. It's amazing how much this picture has traveled around the world on textbooks and Nature and so forth. And it's exactly what we don't want it to have happen. It shows losses. But nobody ever, it is a neat picture. So the Z pulse power facility is located at Sandia National Labs in Albuquerque. And this is the main tech area of this Tech Area 1 at Sandia. And Z is located there. We're in Tech Area 4. So we're out there in that part of the site. And let me just explain pulse power a little bit. There's 2 ways that you can easily get into this high energy density regime. One is lasers. And the other is using the compression of electrical energy into short bursts of high power. And how does it work? Basically, at the heart of it is an energy store device. It's a bunch of electrical capacitors. And these capacitors are charged typically to 90 kilovolts. They're large capacitors, and they typically on Z store 22 megajoules of energy. When you typically, they're called Marx generators because they're charged up in parallel and dumped in series. And so the power levels you can get out of that when their characteristic time of release is about 500 microseconds. And the whole business here is that you take that energy, you charge up other electrical structures, and there are things like intermediate storage capacitors and pulse-forming lines, and the whole idea is to keep going through a sequence of charging. And I hate to use this analogy because a lot of you might not be familiar with it, but it's like a cable pulsar. If you take a cable and you charge it up and you put a switch in it, the characteristic time of the pulse coming out is related to the length of the cable. So what happens here is that we can compress the energy and time in this series that you start with the energy store. You have the pulse forming section. You have laser triggered switches that synchronize all the lines, and you have pulse transmission lines, and you finally take it down to the load. And here you can get these much higher terawatts of compression. Not only that, it compresses it spatially. So this is the whole idea of this is to compress the energy in time and space to get to these regimes that we just talked about. And so the goal, here's one way to look at it. Take the energy equivalent required to operate a TV for a few hours, 1 to 2 megajoules, and compress it in electrical power to provide more power than all the power plants, which is approximately 15 terawatts. Now remember, what's raising the power is the short time. Power is energy over time. So if you divide by a small time, then you get very high powers. And so what do you do with it? We use pulse power drivers to create and study matter of high energy densities. And there's two broad classes. One, we can make Z pinches in various ways to make X-ray sources. And typically this is like 340 tungsten wires that you pass 20 megaamps through, it implodes. I'm going to tell you a little bit more about that. But you get a J cross B force, and it implodes. And so when it implodes, the wire array stores kinetic energy until it stagnates, and then it radiates. And so you can get a lot of soft X-rays. And you can use those soft X-rays just like the lasers to drive hohlraums. And for example, here's two Z pinches on top of each other with a target in the middle. So you can see there's analogy with lasers in the sense that in a laser hohlraum, the laser beams would be heating up both ends of this. And it's analogous. And then we have another approach to this where we embed a target in a low density foam. And this is termed the dynamic hohlraum. And what happens here is the tungsten wire array becomes the wall of the hohlraum, and the hohlraum keeps imploding, and it lowers the surface area of the wall, which will drive up the temperature in the hohlraum. So this is one approach to doing ICF. There's other things that are not shown on here where we try to directly do the Z pinches in a modern high-tech way compared to what James Tuck was doing way back in the 50s. So we'll talk about that here in a little bit. The other thing is to use magnetic pressure. After all, the magnetic pressure is related to the magnetic field by the square. And so it turns out you can generate tremendous pressures, and you can either do material properties experiments with isotropic compression, which Richard is in the process of doing. And I forgot what you're doing exactly, which... I'll talk about the next talk. Oh, it's the next talk, right? I was going to give you a preview of your next talk here. So anyway, material properties. And so he will spend a lot of time on this. So let me just say this. This is showing what I've just said in words. You have a Marx generator, you have an intermediate storage capacitor, pulse forming lines, and typically this part of the machine is embedded in transformer oil, and in the center, the dielectric is water. It turns out deionized water is a great dielectric on short time frames, and it's cheap. So, and then there's a section here where there's magnetically insulated transmission lines, and you say, well, what is that? It's basically a transmission line that's in vacuum. And the currents are so high that when the electrons try to cross the gap, they are insulated by the magnetic field. It's amazing to think of that you can have this transmission line and you're putting megavolts across there, and the thing actually transmits current, because you would think it would just naturally break down. But remember, to break down, the electrons has to cross the gap. And so these magnetic fields are so high that they don't. And so you can see what I'm talking about. Here's something that's discharging on this. This is in nanoseconds in this very long time frame. And then it stores, it just keeps compressing. And the final compression of the whole thing is the wire array itself, when it gathering the kinetic energy and then stagnating. So that was the thing that finally gets you down into the nanosecond time scale. So again, 22 megajoules of stored energy, 26 megaamps of peak current we've upgraded it from these numbers, like 11 and 18, and the rise time is typically 100 to 600 nanoseconds, depending on the load. And so, again, this is like 33 meters across. Now, we also have the Z Beamlet Laser, and let me just go ahead and put these up. In an adjacent building, there is the Z Beamlet Laser, which is taken across, actually between these two buildings, and it's used to form a backlighter for target experiments at Z. And there's also the capability, these are typically a couple of megajoules and, a couple of kilojoule, 2.5 kilojoule laser discharged in about a nanosecond. So it's a pretty healthy laser in its own right. And we're working towards getting a petawatt laser. But the whole idea is we use the lasers, just like in classical ICF, to form various X-ray lines to do backlighting, where we're actually trying to stop frame the implosion of the capsule. And so this, and of course on a laser facility, you just take some of the beam lines to do this, but we don't have a laser, so we have to make a laser to do this kind of thing. So that's, and just to show you some interesting things that can happen, the Z Beamlet and Z petawatt backlighter provides a powerful new capability for diagnosing Z experiments. And I don't want to go into a lot of detail, but we used a spherical crystal imager that has like 10 micron spatial resolution. And it operates at 6 kilovolts, 6.1 kilovolts. And we can see these capsules, and you see some interesting dynamics on the capsule surfaces. And honestly, this is probably one of the highest resolution backlighters there is around. And we're sort of forced into it because Z is a bad, there's a lot of background. There's a lot of hard X-rays, bremsstrahlung. Partially from, I said that the MITLs were perfect. Well, they're not quite perfect. And so you get some electrons that are caused hard bremsstrahlung. And so we have to use very narrow band, like a half EV way to image. And so it works out, the whole system works out that we can get probably the highest spatial resolution in terms of radiographs. And so we know that there's issues on NIF in terms of this kind of phenomena. And I think that, these kinds of diagnostics, and we're trying to do some stuff along these lines on NIF, but the high resolution makes a big difference. And so this opened a lot of people's eyes up. And then the other thing, we can backlight Z-pinches, and they're positively ugly looking. On the other hand, there's very large fields there, and one of the holy grails in magnetic fusion is the ITER project, where you're trying to combine alphas, the alpha heating. Let me say that in these plasmas right today on Z, we can do that because of the very large fields. So I find that interesting. So let's see. Now I'm going to talk about the isotropic compression and shockwave experiments. And there's two styles of this. One is where you gently ramp up the pressure wave, and so the way that works is that current flows like this, and it emits or induces a pressure wave. And these view graphs might be a little dated, but you're talking here 4 to 5 megabar kinds of pressures. Then the other thing you can do is to use flyer plates, and the current drives the flyer plate and up to about 40 kilometers per second, creating pressures up to 10 megabars. And again, I think I'm lowballing these numbers because I think they've achieved higher numbers now. So, and these are used in shock Hugonio experiments, where it's the classic shock flyer kind of technique. And this is an example of the kinds of data, of densities plotted here, and temperature and pressure. And we're typically talking, in the 2 megabar, 3 megabar, and higher kinds of pressures. And since Richard's going to talk a lot about this, I'm not I'm showing this next view graph not to be controversial. This is a classic equation of state measurement for deuterium. And what's happening here is that there's data from Z on here with some lasers, and there's data from some of the laser experiments, and they're very different. And there's probably facets of this that are still being resolved. But the interesting thing is that having a different platform and a completely different experimental approach, we got an issue here, and it shows the value of having independent platforms in doing this kind of physics. And so but it also demonstrates that we can do this with fairly decent error bars, and so this, of course, is all related to equation of state, which impacts lots of different areas in planetary models and ICF and actually primary physics. Magnetically insulated fast Z implosions efficiently convert electrical energy into radiation. Pulse power is a very efficient process in that we can get approximately 15% of the stored electrical energy down to the load, and we can get X-ray powers that are 2 to 5 times electrical. Now, you're saying, again, that's magic, because that's using the kinetic energy of the wire array to do the final compression. And so it's a very efficient process. And this is sort of a schematic, and it's not, but it's sort of a cool one. So I'm going to show you how a wire array implodes. It's a very simple process. You get azimuthal B field, you got the J, the current density coming down the center, and so you get a J cross B force. And so, let's see if I keep going here. Okay, so there's J, current density, there's B, and there's the implosion. Okay, so it's just a J cross B. And you can achieve densities of 1 to 5 times 10 to the 20th per cubic centimeter of 1 to 2 megajoules of radiated energy. This all depends on exactly the load, and 100 to 250 terawatts, and temperatures that range up to 200 eV. And so the real thing that this offers is this very efficient use of the electrical energy. And if you think about a laser, lasers have the incredible ability of focusing to tight spots. But they're not very efficient because at least the flash lamp technology, you have these very large banks, and pumping the laser light is an inefficient process. This is sort of direct, so I just want to give that piece of information out there. So now what I'm going to do now is, okay, so that's the pulse power world and how it works in broad strokes anyway. And now I'm going to talk about how can you use this for fundamental science measurements. And so opacity quantities, how transparent or opaque is a plasma to radiation? In its simplest sense, you can just do an attenuation experiment where you bring photons in, they get attenuated. It's the classic flux that you get through divided by the incident, and it goes like an exponential. So you can measure opacity in a very straightforward way. And so it's interesting that stellar structure depends on opacities that have never been measured. Basically, they're derived from atomic physics models. And so the question is, how good are they? And it's been hard to measure. And the challenge is to create and diagnose stellar interior conditions on Earth. And so we always say we're trying to create a piece of a star in the lab, star stuff in the lab, okay? So how do you actually do that? You can use a dynamic hohlraum to create an X-ray source which both heats the foil and also at the final implosion is the backlighter that supplies the photons for the attenuation. And so Jim Bailey at Sandia put this view graph together, which I find sort of interesting. This is Eddington. So if you guys have been around, if you're around astrophysics in the 30s, he was a very famous guy at Cambridge. And he made this statement: the deep interior of the sun and stars is less accessible to scientific investigation than any other region of the universe. What appliance, I like this, what appliance can pierce through the outer layers of the star and test the conditions within? So Eddington was saying that, well, we do exterior observations, interior plasma properties equals understanding. Jim drew a line through that. Make a piece of the stuff in the lab and do the measurement. And he's been doing this. And so Bob Rosner, who is University of Chicago astrophysicist, says, I love this stuff because I want to know if I'm right, if I'm ever going to be right, because a lot of times the atomic models have really not been tested. So, the sun makes an interesting case because I'm not going to go through all the details here, but the boundary between the radiative zone and what's called the convective zone in the outer part of the sun is very well known. And they use this seismology, helioseismology, to do that. And the predictions of solar do not agree with observations. Solar structure depends on opacities that have been measured. The challenge is to create and diagnose these on Earth. And high temperature enables the first studies of transitions important to stellar interiors. So this boundary is 193 eV and it's about 10 to the 23. That's sort of what the conditions that you want to achieve. And so it turns out on Z, using these experiments, the first round of experiments could achieve about 150 electron volts and about an order of magnitude down. In recent experiments, we've been able to actually get both the temperature and density. And what's sort of interesting is we got reasonable agreement in the first round, but right now it looks like they're not agreeing at all by that extra order of magnitude. So we're still trying to figure this out. It's sort of amazing. And the astrophysics people, I think once this comes out, it's really going to be interesting. Okay, I'm going to switch gears now. I'm going to talk about Z pinches and neutron production. And this is a subject that has a lot of history to it. And to appreciate it, I need to tell you a few things. In 1950s, people put Z pinches on facilities at Los Alamos. They saw neutrons immediately. Classified program, but they found neutrons. It also, people in the UK were doing it at Harwell. Chadwick, who discovered the neutron himself, was a participant. They announced, and the Queen came, and there was a big article in the London Sunday paper of the era. Got neutrons, fusion powers around the corner. And Kurchatov came to England and says, hold on, we're doing the same thing. Remember, this is all classified, so what they could say to each other was sort of interesting. And they decided to have the Atoms for Peace Conference in 1958 in Geneva, and they all compared notes. And they said, we're a long ways away, because what's happening in these systems is that it's easy to get neutrons because there's beams in these systems. It's not all from a hot thermonuclear plasma, because there's instabilities and you get inductive electric fields and you get beamlets that are formed in this thing. And so people said, well, that's not an interesting physics, it's never going to scale right. So people said, we're not going to do Z pinches. And then there's people like us that come along 50 years later saying, well, we should be re-examining this. So the interesting thing is that we've done experiments where we produced about 4 times 10 to the 13th DD. Now remember, that's DT. You have to multiply roughly by a factor of 100 to get the DT equivalent. So, we're talking about yields already of 10 to the 15th. We don't put tritium in there because it's an environmental mess if we did. We've got ideas on doing it later, but the yield follows current to the 4th power. And it's agreement with previous assessment of neutron systems from pinch systems. Our origin of these neutrons is being assessed. And we finally have computing capability now using the particle and cell techniques where we can actually do 3D calculations. And the physics is there. It's the natural physics, and I'm going to talk about it. I think it's pretty exciting. Before, everybody used hydrocodes, whether it made any sense or not. And we knew there's beams in there, so you have to have kinetics in the code inherently to do this problem. And so we're doing these particle and cell calculations, and these are the two experimental references, and this is of using MHD codes. So Pic calculations provide insight into a 50-year-old physics problem. So if you come to Sandia, you're really working on current stuff of the neutron production mechanism in Z-pinch plasmas. And again, there's I to the fourth scaling. Deuterium Z-pinches have been examined experimentally. I told you that all the way for 50 years. And always there's been significant neutron production. Early conclusions had been the majority of the neutron yield is from non-thermal deuterium population that is not scaled favorably. So people just sort of gave up on it, moved to mirrors and tokamaks. But fully kinetic electromagnetic modeling is now possible that includes both non-thermal and thermal processes to address this fundamental issue. And recent Pic calculations of this fundamental plasma are providing new understanding in how neutrons are produced in these systems. One of the experts in the world in Pic calculations is Dale Welch. He doesn't directly work at Sandia. He's with a company in Albuquerque. He's got a commercial code. And we went to him, Bill Steiger and I went to him and said, we want you to do this problem. We want a gas puff. We want it ionized. We want you to put 20 megamps through it, and we want your code to sell. And he says, you're going to get a beam. We said, we know that. That's great. I mean, that was his first comment. You know, and so basically what we're finding is, sure, there's instabilities, there's beams, but there's also the thermal plasma there too. So it's sort of interesting. So any of you that are interested, here's the 3 publications that are on that. But I personally find it very interesting because the standard MHD codes don't include this kind of kinetics. And so basically in this case, you have an E field, you have a B field, you pass the current through it, and it mimics nature, where the particles move just like it, whatever nature tells it to do. It's the best, and it's interesting. So this is a little view graph on the Pic calculations, and I'm not going to go through a lot of the details. But basically, we give them an ionized column of gas, and then we let nature and the code do what it does. They're trying to mimic each other. And we're getting very interesting results out of it. And Dale gave a talk 2 years ago at the Division of Plasma Physics meeting. And we had people that had actually worked on the original Z-pinches, like Sterling Colgate. And he just found this amazing. And he says, he's the one that knew there were beams in there from the beginning, but he thought it was really cool that we picked up on this. And so we did these calculations with both the Pic code and also with a standard MHD code. You get some similarities, but the real problem is that when you look at the neutron energy spectrum, typically you measure the neutron energy width and you interpret that as a temperature. When you've got beams in here, they get spread for other reasons. And actually, the NIF people are starting to worry about this right now because in NIF, you don't necessarily getting everything converging to a point. You can actually get center of mass motion, and that's inherent in these kinds of systems. And this is just some studies of the neutron energy distribution that shows that. And it actually increases as the pinch proceeds. And the neat thing about having this Pic calculation is that you can learn the physics, you can tease the physics out of it. And it's just very fascinating. Now, so Dale's not the only guy doing this. Jerry Chitnam at Imperial College has also got a hybrid MHD Pic code. And he did our gas puff experiments, he modeled it. And he was getting very similar results, 4 times 10 to the 13th yield. But notice that there's anything, these are the trajectories of the alphas inside the pinch. They're very complicated, but it's confined. It isn't like the alphas they can go out vertically, but they are heating the plasma. So the question is, how's this going to scale? And again, the neutron energy spectrum is dominated by thermonuclear reaction, but it has a broad range of energies due to accelerated and magnetized beams of deuterium from his calculations. So this is sort of another independent view of this. And it's interesting. We've also got another concept, magnetized liner inertial fusion, that provides beneficial effects for pulse power driven ICF. And I'm not going to go through a lot of the details here, but lasers can implode things faster than pulse power. It's because of just the nature of the scale size. But one trick that you can do is put a magnetic field in, and it inhibits the thermal conductivity to the wall. It's not confining things in this particular way, but you seed a field in there, and it cuts down on the thermal conductivity, so you can have longer implosion times that better match our systems. And the other thing is that we don't have to go to really high convergence. You know, typically in a hotspot NIF-like target, we're talking 35-to-1 compressions. And a lot of the bad things are happening at those very high convergences. Here we're trying to moderate this so that we can have much lower convergences. And so Steve Slutz has written a Fizerev ladder recently, and I don't have the reference here, but if you're interested, it's out there. And Jerry, not to be stopped, is also looking at these magnetized liners with his hybrid. He's actually, there's Steve's paper right there, the reference. But he's using the Gorgon code that is written at Imperial College, but he also uses, he has a version that runs at AWE, and where they have much larger computers. That's the counterpart lab to the weapons, or to the NNSA labs in England. It's AWE, Aldermaston Weapons Establishment. So he has a collaboration with people out there. So now, I'm almost done, John. So we are developing new pulse power architectures. So Bill Steiger decided, well, what if you could, how much can you push this kind of technology? So this is a design that he actually published in Physical Review. And it's a very detailed paper with a lot of, I know Bill, I know how thorough he is. I think that you could build this thing and it would work as advertised. And this is a petawatt. This is 1,100 terawatt. It's 68 megaamp design. It will operate at 24 megavolts. And the scale here is about 100 meters, which is roughly, you know, the scale size of NIF. And people, you know, it's out there. We could do these kinds of things and get the currents up into that level. So I'm going to finish with this. This is a little dated, but Z is certainly up and operational. Even more extreme conditions are being reached in the dynamic materials program. Several new concepts for pulse power inertial fusion look interesting. That's the things I just told you about. Revisiting all of the pinch stuff. I like to think of it as a plasma you can get your hands around, but it's not ITER. You know, that's this gigantic thing. And it's not as confining as hotspot ignition, where, you know, you've got to make things hot in a very thing. So I think it merits, and I think a lot of community, or a lot of us in the community are thinking that it merits another look. I mean, it's a 50-year-old system. It was a good system in a way when it was born, but, you know, driving it with this modern technology is very interesting. So higher currents are enabling brighter X-ray sources and hotter and denser for astrophysics. I hope I've convinced you. There's a whole slew of astrophysics experiments that I didn't talk about here on white dwarfs. There's just a lot of warm dense matter experiments that are happening. So I'm just giving you a sample. And the Pic calculations of gas puff Z-pinches reveal new insights into, quote, a classic system. So I'm going to end on that. So.